Alright, so in this video we are going to talk about formation of differential equation, and before I start talking about it, let's pause and ponder why at all we need to form a differential equation, right? What was the necessity that a differential equation should be formed, right? Now to explain this concept, let's go back to the origin of the formation of equations. Let's forget about differential equations. Let's just talk about why at all there is a need to form equations, right? So when we say the equation of a straight line is y equal to, let's say, x plus 2, right? What do I mean by it? Now let us understand this, because if we are able to answer this, we'll be able to answer the fact why at all a differential equation is formed. What was the need for a differential equation? Now, in the beginning of the geometry, when we wanted to represent some set of points, right, or we wanted to show a path. For example, if I say that I am treading on a path whose coordinates are 1, 3, 2, 4, 3, 5, 4, 6, and so on and so forth, right? It's very difficult to actually write those infinitely number of points which actually I am treading. Okay, so instead of writing these points as one by one, we can actually say that I am treading on such a path where the x coordinate and the y coordinates of the points on which I am walking are related to each other by this relation. So if you choose x as 1, y automatically becomes 3, which is this point, correct? If I take x as 2, y automatically becomes 4, which is this point. So instead of saying all these points which are infinitely so many in number, I can simply say that I am walking on a line whose equation is y equal to x plus 2. Isn't that a much easier way to express the path which I am walking? So that straight line, instead of saying I am walking on a straight line which is made up of point 1, 3, 2, 4, 3, 5, 4, 6, it's simple to say I am walking on a line whose equation is y equal to x plus 2, isn't it? So this is nothing but a relation which connects the x coordinate, this is nothing but your abscissa, this part, and the y coordinate, which is nothing but the ordinate of this point. So 1 and 3 are related to each other in this fashion, just like 2 and 4 are related to each other in this fashion. In a similar way, even for differential equations, right? If I ask you this question, dy by dx is equal to, let's say, 2x, right? So this is actually a differential equation, correct? Now if I say this is a differential equation which is valid for the curve y equal to x square, correct? Everybody knows when we find the derivative of x square with respect to x, my answer will be 2x. Somebody else can say it is also valid for a curve x square plus 1, right? Somebody else can say it is also valid for the curve x square minus 5, right? So in general, I can say the same differential equation is valid for all those curves which are of the type y equal to x square plus c, where c is an arbitrary constant. You can choose your c anything you want, and this differential equation will still be valid for that. So in order to explain differential equation in one line, I will just say differential equation is nothing but a representation, or I would say an aggregate representation of a family of curves. That means a set of curves which belong to the same species. So here if you see, it's a parabola. So all the parabola which belongs to this species is collectively categorized as this differential equation, right? Just like all the set of points which satisfy equation that your y coordinate is 2 more than the x coordinate is collectively specified as this. right? So this brings me to a very important concept in differential equation called the solution of a differential equation, right? Now solution of a differential equation, I will talk about this in the later part of this video, but as of now, just to give you a heads up on this particular curve is a solution to this differential equation, correct? Because this satisfies this differential equation, or in other words, this differential equation has been formed for this curve, or has been formed from this curve. Okay, so we are going to talk today about how to form a differential equation once you know the solution. So once this has been mentioned to you, how do you form a differential equation? Now it may sound very easy to you, you just have to differentiate it and get the answer, but however there are some set of rules which you need to keep in mind while you are forming differential equations, which I'll be talking in some time. Alright students, now we'll talk about how to form a differential equation. In the previous section we had talked about why at all we need a differential equation and what does it represent. Now we'll talk about how a differential equation is formed. Now you can see on your screen that I have listed out the 3 steps that we need to follow in order to form a differential equation, right? Now a differential equation is formed for a family of curves, right? So basically a family of curves will be either given to you, or a situation will be enlisted out from where a family of curves can be generated, right? So to keep the case simple, I will give you a family of curves and then we'll learn how to form a differential equation from it. Okay, so let us talk about an example where I have given you a family of curves as y square is equal to 4ax plus b. Okay, anybody can guess here that I am talking about a family of curves which represent parabola, right? Here your a and b are arbitrary constants. A and b are arbitrary constants. Okay, so your a and b are like parameters which keep on changing, and as it changes they keep on representing different parabolas. However, all those parabolas belong to the same family. Okay, now let us follow the steps which I have listed out. The first step is I need to differentiate this equation or the equation of the family of curves as many times as the number of arbitrary constants involved. Okay, now this has a very important relevance. This says that your order of the differential equation that is going to be formed should be equal to the number of arbitrary constants involved in that curve's equation. I'll repeat this again. The order of the differential equation that is getting formed should be equal to the number of arbitrary constants involved in that equation. So in this equation we can see there are 2 arbitrary constants involved. One is a, another is b. So this will result into a differential equation whose order will be 2. Why? Because there are 2 arbitrary constants. So I can write here order should be equal to the number of arbitrary constants involved. This is very important. So the order of a differential equation that you are going to get formed should be equal to the number of arbitrary constants. Alright, now how do we form the arbitrary constants? How do we form the differential equation? In the differential equation we differentiate, and in step number 2 we try to eliminate the arbitrary constants in that given equation. So while you are differentiating, you will keep on getting some equations which along with the original equation you can use to eliminate the arbitrary constants. So a and b have to be finally been removed. Okay, after that the eliminant, that is whatever is left after having got rid of the arbitrary constant, will be the required differential equation which we need. So let us apply these 3 steps on this problem so that things are clear. Let us differentiate once. So what is the derivative of y square with respect to x? We all know chain rule. So derivative of y square with respect to x will be 2y dy by dx. Right? Derivative of 4a x plus b will be nothing but 4a. Right? We can get rid of the factor of 2 from both the sides. So I can drop this 2 factor here. and write it as equal to 2a, right? Now I have already got rid of b. Now the only thing which I need to do now is get rid of a. Simple. To get rid of a, I will differentiate it one more time, because I have a liberty to differentiate as many times as the number of arbitrary constants. So since there were two arbitrary constants, I have a liberty to differentiate it one more time, because one time I have already done. So let us differentiate both sides again with respect to x. Now care should be taken while differentiating this with respect to x. When we are differentiating y dy by dx, I'll be using which rule? The product rule, exactly. So I'll be using this and this as two functions, u and v, and I'll be applying the product rule of differentiation. So let us take y times derivative of dy by dx. Now guys, please note, the derivative of dy by dx with respect to x is nothing but d2y by dx square. So I'll have y d2y by dx square, okay, plus keep dy by dx as such, into derivative of y. Derivative of y we all know is dy by dx. So I'll have again dy by dx coming over here, isn't it? And 2a derivative we all know is going to be 0. A being a constant, though it's an arbitrary constant, but it's a constant, so its derivative will be equal to 0, right? So simplifying this further, I can say y d2y by dx square plus dy by dx whole square is going to be 0. This is the equation which is actually the differential equation which corresponds to this family of parabola, right? So this is your answer which we need to obtain. So again, repeating all the steps in the order in which you have to follow. You have to first start with differentiating the curve. You can differentiate it one by one, but you have to differentiate it only as many number of times as the number of arbitrary constants involved. So if the number of arbitrary constants are 1, you can differentiate it only once. If there are 2, you can differentiate it twice, right? It should not happen that there is a 1 arbitrary constant and you are differentiating it 2 times. That should not occur, right? And while you are differentiating, you will keep on getting equations, right? Using the equations along with the original one. Right? Many students make a mistake. They forget to use the original equation given to you. No, you can use the original equation along with the equations that you are getting while you are carrying out the process of differentiation, and use them all to eliminate the arbitrary constants. By hook or by crook, I have to get rid of a and b. Right? In this problem, I have to get rid of a and b. So all the arbitrary constants have to be got rid of. After having got rid of all the arbitrary constants, the eliminant, that means the remaining thing. For example, here this is the eliminant. This eliminant represents the differential equation for this family of curves. In other words, this differential equation will be satisfied by this curve, or this differential equation has been formed for this family of curves. Just two ways of looking at the same thing, right? Hope this process of forming the differential equation is clear to you. Alright guys, so hope you have tried this question on your own. So now we'll be solving this question for you. As you can see, this is a family of curve y equal to a e to the power 3x plus b e to the power x, right? Why it represents a family? Why not a single curve? Because we have a and b as arbitrary constants. So these constants will keep on changing, and as they change, they represent different curves of the same family. Okay, now we have to form a differential equation which satisfies this family of curves, or in other words, the other interpretation is find the differential equation which is formed from this family of curves. Okay, now since there are two arbitrary constants, I have a liberty to differentiate it 2 times, correct? So let us start by differentiating it once first. So dy by dx will be nothing but a times the derivative of e to the power 3x. Now derivative of e to the power 3x will follow the chain rule. So it will be e to the power 3x times 3. So let me write 3 over here. Okay. Plus derivative of b e to the power x will be b e to the power x. Isn't it? Okay. Now here if we see this equation we have not been able to eliminate any of the arbitrary constants involved. So A and B are still involved. Alright. Now what we will do in this case now, I will try to reduce the number of constants here. For example, this b e to the power x I can replace by y minus a e to the power 3x. Right. So what I mean to say is that I can replace b e to the power x as dy by y minus a e to the power 3x. Alright, so I'm going to replace it over here. So I can say dy by dx is equal to 3a e to the power 3x plus y minus a e to the power 3x. Right? On slight simplification, I can club these two terms and write it as dy by dx equal to 2 times a e to the power 3x. Right? Now let us differentiate it once more time. So once more, if I differentiate, I'll get d2y by dx square equal to, now this will be 2a e to the power 3x into 3. So I can say this into 3. Okay, plus dy by dx. Correct? So I've used the chain rule over here, and y derivative is dy by dx, and of course dy by dx derivative is d2y by dx square. Okay, now again this term is appearing over here, right? So what I will do now, I will replace 2a e to the power 3x with dy by dx minus y. dy by dx minus y. Okay, where? Here, at this location. Alright, so what I will get now, d2y by dx square will be equal to 3 times this term, which is nothing but dy by dx minus y. Again I have a plus dy by dx waiting outside. Okay, now as a result you see that we have got rid of all the arbitrary constants here. Do you see any a, b in this equation? No, we don't. So we have got rid of arbitrary constants, and at the same time I have taken care that I am differentiating it only twice. Why? Because there are 2 arbitrary constants. So summing this up, we can conclude that the differential equation formed for this family of curves will be d2y by dx square equal to 4 dy by dx. Why 4? Because there is a 3 dy by dx here and 1 dy by dx is over here, minus 3y. Okay, so this is the differential equation for the family of curves given by this. Okay, so by this time you would have realized that formation of differential equation is not a straightforward activity, right? You have to apply your all sorts of strategy to get rid of a and b, right? And you're working under the constraint that you cannot differentiate it as many number of times as you want, right? You have a limitation that your derivatives or the number of times you are differentiating should not exceed the number of arbitrary constants. Alright friends, in this question, this is a slightly differently framed question where you have not been mentioned the family of curves, right? So you are instead asked to find the equation of a family of curves and then obtain a differential equation out of it, right? So the question says you have to write the differential equation for the family of curves or family of circles which touches the x-axis at origin, right? Now let us understand this. So let's say this is our x and the y-axis. Okay, so there is a circle which touches the x-axis at origin. So I can have a circle like this, right? I can also have a circle like this, right? I can also have a circle like this. So there can be so many circles which I can draw which will touch the x-axis at origin, right? And we have to write a differential equation which signifies all these family of circles. Correct? So the first thing is I need to write down a family of such circle's equation, right? How do I write that? Very simple. I can assume the center of this circle to be, let's say, 0, comma a. Why 0, comma a? Obviously, when it is touching the x-axis at origin, that means a line perpendicular from the origin should pass through the center of the circle, and any line perpendicular to the x-axis has to be the y-axis, right? And it is passing through the origin. So any line which is passing through the origin and perpendicular to the x-axis has to be the y-axis. So in other words, the center of the circle lies on the y-axis. So I can assume the center to be some 0, comma a, correct? And not only that, you will also observe that the radius of this circle will also be a. Now what is a? A is some arbitrary constant. Why? Because I'm not sure which circle I'm talking about, whether I'm talking about this one or this one or this one or others to come. So this A is something which is varying, and because it is varying, I'm calling it as an arbitrary constant, right? Because it can be anything, it can be arbitrary, right? So the equation for such a circle whose center is at 0, comma a and radius is a can be written as x minus 0 whole square plus y minus a whole square equal to a square, right? So you all have done circles in class 11th, so everybody is familiar with the equation of a circle whose center and radius is known, correct? Now, so I have one arbitrary constant here. Please note, there are no two arbitrary constants, only one arbitrary constant is there, which is a. So a here is an arbitrary constant, and therefore I have a liberty to differentiate it how many number of times? Once, because there is only one arbitrary constant. Many students make a mistake, they think there is an arbitrary constant here, there is an arbitrary constant here. No, you have only one arbitrary constant in this particular problem. So I can differentiate it once. So let us do that. What is the derivative of x square with respect to x? We all know it's going to be 2x, right? Derivative of y minus a whole square is 2y minus a times dy by dx, correct? The derivative of a square with respect to x is going to be 0. Okay, now we can drop the factor of 2 from everywhere. So let us drop the factor of 2 from everywhere. So 2 can be dropped off, right? Now I need to somehow use this equation and the given equation. So basically, let me name it. I can use 1 and 2, right, in tandem to eliminate what? Eliminate the arbitrary constant, which is a, right? So how do I do that? Very simple. I can write this as a minus y dy by dx equal to x. Okay, so all I have done, I have brought the x on this side, which is minus x. I change the sign both the places. In other words, a minus y is nothing but x by dy by dx. Okay, in other words, a can be written as y plus x by dy by dx. Okay, right? So we can simplify it further to x plus y dy by dx divided by dy by dx. Alright, now having obtained a in terms of x, y and dy by dx, I will do a simple activity. I will replace this back in equation number 1. Okay, so I will substitute a, let me call this as the third equation. I will substitute a from 3 in 1. Okay, so what I'm going to do now, I'm going to substitute this value of a in 1, right? But before that, let us simplify it. If I simplify it, I'll get x square plus y square minus 2ay equal to 0. Okay, having done this, let's substitute the value of the value of a. So the value of a from there, I can write it as 2y times x plus y dy by dx whole divided by dy by dx equal to 0. Correct? Now, it's a good practice that you should not leave a dy by dx in the denominator. So let us multiply throughout with dy by dx. So which gives you dy by dx times x square plus y square minus 2xy minus 2y square dy by dx equal to 0. Right? I can take dy by dx common over here. So which finally gives me x square minus y square dy by dx minus 2xy equal to 0. So this gives you that final eliminant, that is the differential equation that satisfies all these family of circles. So this satisfies all the curves which is in this family of circles. Right? So this is the differential equation where you have seen that I have not differentiated it more than once. So you can see the order of this differential equation is 1. Remember order? It's the highest differential coefficient that occurs. So it's 1 here. Differential coefficient means dy by dx. And all the arbitrary constants. Here we had only one arbitrary constant a. It has got eliminated. Right? So this is our answer for this problem. Alright friends, so when this question was asked in the exam, many students wrote the answer for this as 4. Right? The order of this differential equation is 4. Right? And if you have done the same, please let me tell you, you are wrong. Right? Why it happens? Why this differential equation, or why the differential equation that is to be formed for this family of curves does not have an order of 4, right? It's not a simple rule that we count the number of arbitrary constants 1, 2, 3, 4 and write the answer as 4, right? In order to find the order of the differential equation, whose solution is this, we need to see what is the effective number of arbitrary constants involved, which cannot be obtained by just counting the number of arbitrary constants written in that curve's equation. We need to see effectively how many arbitrary constants are involved. Now, in this question, if you see it very closely, these two arbitrary constants can actually be treated as one arbitrary constant. So even though it is C1 plus C2, effectively it is just one arbitrary constant which is involved, right? So we can write this first of all as some arbitrary constant A. So I have clubbed C1 and C2 and written it as A, e to the power x. Okay, here also if you see, I can write this as C3 e to the power x into e to the power C4. Okay, now C3 into C4, they will also multiply to generate only one arbitrary constant, right? We cannot write this as two arbitrary constants. So this is a constant, agreed, this is the constant, agreed. Their multiplication will effectively, the word is effectively, will generate only one arbitrary constant. So I can club them and write it as b e to the power x, right? Not only that, e to the power x, if I take common, I can write it like this, right? Now a and b both are arbitrary constants. So when these two arbitrary constants are joined, I'll get another constant, right? So I can call this as another arbitrary constant, let's say capital C, right? So in short, if you realize, the effective number of arbitrary constants involved are only 1, right? So this particular family of curve, or this is a solution to a differential equation whose order should be equal to 1, right? So the answer is 1 in this case.